Extraction of metals at middle of activity series. 1. Extraction of lead. 2. Extraction of iron, blast furnace. 3. Extraction of copper. 4. Extraction of titanium. 5. Extraction of iron, thermite process. Extraction of lead.
Lead is a bluish grey metal with a bright luster. It is a soft metal. It can be cut with a knife, drawn into a wire and rolled into a sheet. It is not a good conductor of heat and electricity. Melting point of lead is 327.5 degrees Celsius or 621.5 degrees Fahrenheit. Lead ore is most commonly found as lead sulfide, that is PbS, is known as galena. There are two steps involved in the extraction of lead. One is concentration, 2 is roasting and smelting in a reverberatory furnace. Roasting. Roasting is a pyrochemical reaction where ore is heated in the presence of oxygen below its melting point. Roasting transforms sulfide ores into oxides. Concentrated ore, that is galena, is taken in the reverberatory furnace. It is roasted and smelted at moderate temperature in the reverberatory furnace. By regulating the air supply, the temperature of furnace can be controlled. Lead sulfide is heated in the presence of excess oxygen in the reverberatory furnace below its melting point. Lead oxide is obtained and emits sulfur dioxide. Further, by treating lead oxide with coke at 1400 degrees Celsius, it reduces into the pure lead metal, liberating carbon monoxide. Pure lead is collected from the furnace. This process is called as smelting.
Extraction of iron, blast furnace.
Iron is silvery grey metal with a luster. It is malleable and ductile. It is a good conductor of heat and electricity. It can be converted into permanent and temporary magnets. Iron metal is most commonly found as iron pyrite, that is FeS2. Iron metal can be extracted from iron pyrite using blast furnace in two steps. One is roasting and the second one is smelting. Roasting. In step 1, iron pyrite is roasted in blast furnace, gives hematite, that is Fe2O3, and emits sulfur dioxide. Smelting. In step 2, hematite ore is charged from the top of the blast furnace. Ore is mixed with flux, that is limestone, and fuel, that is coke, as shown here. Hot air is also blown into the furnace. When coke is burned, temperature rises up to 2200 Kelvin. Coke gets oxidized to carbon monoxide. At 500 to 800 Kelvin, ferric oxide, that is Fe2O3, reduces into ferrous oxide, that is FeO, and liberates carbon dioxide. Simultaneously, flux decomposes into calcium oxide and liberates carbon dioxide. This calcium oxide reacts with impurities of the ore, that is silica, and forms slag in the molten state. Molten slag is separated from the furnace. At high temperature ranges such as 900 to 1500 Kelvin, ferrous oxide reacts with carbon monoxide and forms iron in molten state. Or ferric oxide Fe2O3 reduces to iron and carbon dioxide. Molten iron sinks to the bottom of the furnace. It is collected from the outlet of the blast furnace. The iron obtained from the blast furnace contains about 4% of carbon and many other impurities like sulfur, phosphorus, silicon, and manganese in smaller amount.
Extraction of copper.
Copper is tough, strong, and soft reddish metal. It is ductile, antibacterial, non-magnetic, and is a good conductor of heat and electricity. Its melting point is 1083 degrees Celsius. In nature, copper is available in three different ores like copper glans, that is Cu2S, copper pyrite, that is CuFeS2, and cuprite, that is Cu2O, that is ruby copper. But predominantly, copper is extracted from copper pyrite, that is CuFeS2. Treating of copper pyrite with air in the reverberatory furnace between 500 degrees Celsius and 700 degrees Celsius leaves copper sulfide in the furnace. Further, supplying air to the furnace, copper sulfide oxidizes into copper oxide and emits sulfur dioxide. Now, let us stop the air inflow and increase the temperatures in the furnace. Then the rest of the copper sulfide and copper oxide react with each other and produces copper metal. In this reaction, sulfur dioxide liberates and escapes through the chimney. In this process, 98% pure copper can be obtained. Pure copper metal is collected from the furnace.
Extraction of titanium.
Pure titanium is a lustrous white metal. It is a weightless metal. It has high strength, stiffness, toughness with low density. It is strong metal with good corrosion resistance. It is being used in manufacturing of aircraft parts. It is abundant in nature. Titanium cannot be extracted by reducing the ore using reducing agent carbon, as this forms a titanium carbide, that is TiC. The presence of the carbide makes the metal very brittle, so that an alternative reducing agent must be used to extract titanium. Wilhelm J. Kroll developed the process to extract titanium using highly reactive metals such as sodium or magnesium as reducing agents. This process is well known as Kroll process. In this process, the ore, rutile, impure titanium 4 oxide is heated with chlorine and coke at a temperature of about 900 degrees Celsius produces titanium tetrachloride in liquid form. The pure liquid titanium tetrachloride can be separated by fractional distillation process carried out in the presence of argon or nitrogen atmosphere. Reduction. This pure liquid titanium tetrachloride and molten magnesium are taken in a boiler and heated. This reaction is carried out under argon. Magnesium replaces titanium and produces a porous titanium sponge and magnesium chloride. This is an exothermic reaction. The magnesium chloride is drawn out by distillation under very low pressure and at high temperatures. Titanium sponge is left over in the boiler. It contains 30% of impurities in the form of magnesium chloride, that is MgCl2. Titanium sponge is heated at high temperature to remove impurities from it. Later, titanium sponge is melted in the presence of argon to produce pure titanium slabs. Similarly, titanium can be extracted by using sodium as reducing agent at about 1000 degrees Celsius instead of magnesium. In this reaction, sodium replaces titanium and forms titanium and sodium chloride.
Extraction of iron, thermite process.
The reaction of metal oxides with aluminium is known as thermite process. In this process, when highly reactive metals such as sodium, calcium, aluminium, etc. are used as reducing agents, they displace metals of lower reactivity from the compound. These displacement reactions are highly exothermic. Let us see welding of rail with iron extracted by the thermite process. Install the welding setup at the broken part of the rail. Pour the thermite mixture, that is mixture of hematite and aluminium, at the bottom of the metal container. Now, Pour powder of magnesium and barium oxide above the thermite mixture. Place the metal container over the welding setup as shown. Introduce a magnesium ribbon into the metal container. Ignited magnesium ribbon catches fire immediately. This fire initially ignites the top loaded mixture of magnesium and barium oxide and mixture of hermite later. Aluminium displaces iron in the ferrous oxide and left pure iron in the molten state in the metal container at 2000 degrees centigrade. This molten iron sinks to the bottom of the metal container, gets released into the broken part of the rail. After rail gets attached, its surface is smoothened. This is also an exothermic reaction. Chromium can also be extracted from thermite process.